Okay, today's lesson is a application of how these fields can be used. And so here we've got electric motors. So there's a couple of videos there, simple DC motor explained and the working principle of the DC motor. The second one there's an animation which is quite good. So an electric motor essentially has two aspects. It has a coil with electricity goes through it, and what that happens then, that produces a magnetic field. And the other aspect of it is that it's got a permanent magnet. Which of course has a magnetic field. So as you can imagine, we've got two magnetic fields and they can interact with each other. So effectively this little graphic here very simply says what happens. Right, so you've got current in a wire which creates a magnetic field which interacts with another field which produces a force on the current carrying wire which makes it rotate. Essentially that's it. Alright, so if we have a look at this other diagram, this one here, alright, so here's our current flowing through our coil going in that direction. We've then got the permanent magnet, so we've got magnetic fields going across there like that. And if we, so current, that's the current flowing that way, and as if we use our I to B, force gives the direction, and as that's shown over, when you do that into the page, curl your fingers to the, your fingers in the direction of field current into the page, and so your hand pushes down. So on this side of there, you've got a force acting down. So therefore you get rotation. And in the other side, with the current flowing out of the page, so your fingers, thumb points out of the page, fingers north to south, your palm points up, so you have a force acting there like that. And so that's all very nice. And so you get some rotation. So there's position 1, then we get across to position 2, it's rotated, and as you can see we've still got those forces acting in that direction. And then we get to position 3 where it's rotated more, and so now the coil is perpendicular to the current, and we've got force up and a force down. So if it's got enough momentum, it'll rotate past it, but the issue is even our current is still flowing in the same direction, so we've got force acting there. So what we need to do, as this diagram, this bit over here shows, we now need to reverse the current. So remember here the current's going in that way and out that way, so because if we don't reverse the current, those forces are just going to pull that coil in this direction up there, and then what's going to happen, it's going to get stuck like that, which we don't want. So if we reverse it so that we now have on this top one the current going in and the current going out there, the force will change direction, and so it would keep continuing to rotate. So in the notes there, there's a lot more detail on that. So, question is, how do we actually get it to change direction? So, here's a diagram that sort of shows that. Alright, so here's the diagram that shows that. So, here's your battery down here, and so your current's flowing there to these things that are called brushes. Usually they're made of carbon, and then they touch this thing here we call, that's split. It's like a ring, but it's got a split in it, and so it's called a split ring commutator. So at the moment, what's happening is that the current's coming in here, it's going around there, and it's going this way. And so we're getting our force in the down direction, like so, and we have the thing rotates. So as it rotates, then the split ring commutator will rotate also, and then what eventually happens is that this ring here rotates far enough so that it no longer contacts that brush, but this one over here. Alright, so here's some diagrams that show that a bit better. Alright, and these diagrams are in your notes. So here we've got into this, so the current is always flowing in that way, and it's always flowing out that way. Alright, so it shows here with this particular one, we have rotating that way. And so you'll notice too also we've got this split, and we've got this one over here. So when they rotate a bit, there's that grey one I've got, and here's the black one. So you'll notice the black one now is just hanging on the edge here, in there. And when it rotates a bit more, because it'll have some momentum, the black one is now contacting where the current's going out. So down here the current was going into the black one, now over here the current's going out of the black one and into the grey one. Alright, so what that now does, it's now changed the direction. So instead of like over here, side AB, the force was up. Now here's side AB there, right there, and then a little bit of momentum takes it over. There's side AB, and now the force on side AB is down, and it continues to rotate. So the thing that does it is what's called there it is, the split ring commutator. Let's get rid of all of that stuff. Alright, this is it right here, the split ring commutator. So what does it do? It reverses the current around the loop, and by doing that the force changes, keeps the thing rotating. If we didn't have that, then eventually this middle one here, this diagram here, would sit in that middle position eventually if we didn't have it. Alright, so again in your notes there's more diagrams, more detail I should say about that. Alright, so if we can get this thing rotating, which we can without too much trouble, as you've seen, and you've watched those videos, so you can see more explanation than what I'm doing on the videos, we can get some rotation. So the good thing is we use these motors because they can provide a force, right? So Elon Musk, and with his Tesla cars, and there's others with other electric cars as well, but he's one of the most well-known ones. They can provide a force. Now, the force, when it's when it's causing something to rotate, we call that force a torque. So, say for example, we have current going out, current going in, and here's the centre. I'll mark that in blue, there's the centre. Then from that there to there would be called R. This here would be our axis of rotation. And let's say, for example, if the field that it's in causes a force up here and a force on the other side of the wire down that way. So what's going to happen is that this coil is going to rotate. Oops, rotate. No, going to rotate. That coil's going to rotate. All right, and that rotation is called a torque. Now that torque relies on the force, but not only the force, and so the torque is used by the letter tor, which is that, and it is force times r, the radius, so the distance from the centre to where the force is acting. Alright, and so that's the torque. Alright, and it's torque that's important, not just force, when we're talking about electric motors. So let's go over the page to a bit more, and so in your notes here, in 1.3 torque, there's a few things about torque. So first of all, torque is force times the radius, and so the unit for torque then is just a combination of those, Newton metre. Alright, it's a bit ugly, let's do that with the proper R. Is Newton metre, just combining those two things together. Now, of course, the force created by the wire, alright, so here's our, back here, here's our wire. Alright, so here's our wire there with the current flowing through it. So the force created by that we know from previously is N equals, it's not N equals at all, it's F equals N I L V. Alright, so the torque then produced by a wire in a magnetic field would be the force times the radius, so NILB times the radius. Right, so there's a few things that we can do, and it talks about it in the notes, because torque is directly proportional to the speed of the motor. So we've got to increase the speed of the motor by increasing the torque. An R on there, it's a bit ugly, let's replace it by a good looking R. Alright, so what can you do? You can do a number of things. So this N, of course, is the number of coils. So you can increase the number of coils. The current, you can increase the current flowing through it, and then, you know, there may be limitations to that within certain applications. What else can you do? Well, you can increase the length of the coil or the wire in the magnetic field. Again, there may be certain limitations, and we can increase the permanent magnetic field. Again, in certain applications, there may be limitations to that. And then finally, the other thing, you can look at how far that wire is in that coil from the centre of the rotation. So again, there may be limitations in that, and they go through that in your notes, what the limitations would be. And essentially a lot of it gets down to the size of the motor. Just to make that bigger, that bigger, that bigger, you're going to have to increase the size of your motor. Your current, to increase that, well, you can do that, but then you need bigger batteries to supply. And the other thing is the magnetic field, well, you need bigger magnets to increase that. So again, as I said, certain limitations to what you can actually do. But anyway, so that's what our electric motor, it depends on all of those things. So let's have a look at an example. Alright, go back to this diagram. So this diagram up here, the coil shown, square of side length 4 centimetres, consists of 20 turns, carries a current 5 amps, field of 0.8 Tesla. Alright, first thing first. When I look at that, I notice one thing, straight away that the units are not in our standard units that we need to use. So kilogram meters seconds, and that is this 4 centimetres. So our length is 4 centimetres, which is 0.04 metres. So when we get to do the calculation, we need to make sure about that. Alright, so part A says, what are the forces on each side? So there's two forces, there's that one that side and there's that one that side. So it's talking about just each side. And so the force on each side, force equals NILB. So when we go back and have a look, our number of turns, it said, was 20. The current is 5 amps. The length of the wire is 0.04 metres. And the magnetic field, 0.8 Tesla. So we multiply all of that together and we get 3.2 Newton each side. Alright, so that's what it's asking for, each side. Alright, part B. Part B says, what is the torque on the coil? Alright, so torque we know is, oops, I don't know why I did that. Let's get rid of those. Torque, as we know, is force times the radius. Now the question is, what is the radius? Now when we go back and read the question, it says a square of side length 4 centimetres. So that's square, all those sides are 4 centimetres. So from here to here is our radius, and if that was 4 centimetres for the whole side, the radius then would be 2 centimetres from the middle, because rotating about the middle here, which of course is 0.02 metres. Alright, so that looks simple enough. So it's 3.2 by 0.02. Write the right thing back here. Yep, I did. Now, that's there's two sides that the force is acting, that one and that one. So, and I said that here, each side. So this one here, what I've got here, that's just for one side. So because there's two sides on that coil that have a force on them, I need to then times that by 2. So that then takes into account each side. And when I do that and multiply that on my calculator, I get 1.128, and the units are Newton metre. Alright, so that's it for motors. It's important that you work through and you understand this. I can almost guarantee you there's going to be some sort of motor question in some form or another on the exam. So you need to know it. So there's some text questions on page 92, and then there's also some past exam questions that for you to look at. Alright, you might not get, there's a lot there, so you may do some and then come back later when you're doing revision for others. Alright, so whatever you don't understand, make sure you ask. Don't forget those videos on the website, and also my notes if you missed anything that need to fill in there on the website too.